So we had a fun time drawing the sun last time. I thought it might be a fun series to start drawing the planets one by one. So tonight, it's going to be Mercury. In doing a little research for this video, there's actually a ton of really interesting things about Mercury that I had no idea. To me, it was always kind of the most boring of all the planets. It's the smallest, for one. So that's kind of a strike against it right away. Seems to have the least, Venus has a thick atmosphere, it's the hottest. Mars is the most like Earth, I guess. It's got the highest probability of a place we might colonize, according to Elon Musk and many others. And then they got the gas giants, who just have sheer enormity going for them. So I was pleasantly surprised and actually definitely won over when I discovered all these interesting facts about Mercury. So let's touch upon the mythology, the history of our observations of Mercury, and then we'll transition into the actual science and elaborate on what it is that we know, all the way up to the most current probe, the Messenger probe. Mercury is one of 6 planets we can see with the naked eye, the others being Venus, Mars, Jupiter, Saturn, and if you look outside, of course, Earth. And while our distant ancestors probably didn't realize the planets were light years closer and millions of times smaller than all the other little holes to heaven they might have witnessed in the night sky, they were no dummies. They really just hadn't separated their knowledge of how we should act from knowledge of how less complex objects in the world do act. That being the distinction between morality and values, the things we get from spiritual wisdom, and objective, data-based observations about phenomena in the world. They hadn't developed technology to probe deep into the heavens, but they certainly observed how through the seasons say we have a constellation, Orion's belt. And there were certain points of light in the sky that wandered around, that moved a little differently with respect to all the other stars in the sky. So you might have Orion's belt showing up in the same spot of the sky night after night for a certain duration throughout the year. But then you have a slightly brighter planet. This thing that really looks like a star to the naked eye, moving with respect to the background, the more fixed background. Say 8 p.m. every night. I'd really bet that our ancestors ancestors, going back maybe 100,000 years, maybe 1,000,000. I really believe that they would have picked up on this and paid special attention to these wandering stars. You know, light pollution from the cities sadly drown out the glory of the night sky for most of us. But if we were to look at the night sky in a much more rural area, it would be pretty obvious to us, this movement of Mercury, Venus, Mars, especially Jupiter and Saturn. You know, I always like to imagine what it might have been like that far back in time, and what kind of awe the stars looking up at night, you know, must have invoked in our ancestors, given that, you know, with all our knowledge, it's really still almost overwhelming how amazing it is to look into the sky at night, on a clear night, and see these points of light that we know are, you know, hundreds, or at least tens of thousands of light years away. We have a scientific understanding, but to our ancestors it must have been just a true mystery, you know, really what it was that these things were. They're so intangible, they're so far off. They must have imbued them with a certain spiritual sacredness, undoubtedly. So we're going to go back maybe 10 millennia or so ago in the past, briefly, and experience a special moment for an ancient Mesopotamian astronomer. But first I wanted to give us a little outline of this area. Maybe we'll do Africa here. And going over to Israel, Eastern Mediterranean. And then we have Turkey, leading west into Greece. Greece's little outcrop, the Peloponnesus, Lower Peloponnesus, which goes into, I think, the Adriatic, the Aegean, the Adriatic, and then this becomes the boot of Italy, Sicily, and going more west, we have France, and then Spain and Portugal. And then from this perspective, maybe Northern Europe vanishes over the horizon. So let's go ahead and bolden these lines real quick. And you guys might be wondering why I'm focusing on Earth if this is a video about Mercury. And that's because Mercury got its name from the ancient Romans, who got their god Mercury from Hermes, who is a remnant of much older traditions from the Near East, in Egypt. Let's see. Got the Red Sea here. And going back to one of the oldest known civilizations we have over here, between the rivers that come from these mountains into the Persian Gulf. We have the Caspian Sea over here. This civilization here is Mesopotamia. And just something as simple as the name Mercury has such a deep history that I wanted to share it with you guys. So let's be sure to draw Cyprus, Crete, right there. And let's shade in the oceans real quick. Then we have the Red Sea down here. Persian Gulf, the Caspian Sea. We don't want to forget the Black Sea up here. And then we have the Nile Delta right there. Alright. So just imagine this. Just imagine we're up early, before the birds and the sun. We grab a quick bite of bread and head out the door of our little hut into the darkness, to the nearby fertile banks of the Euphrates River. Make some little sawgrasses right there. And oh look, there's Ishtar, which is Venus, near the horizon, and shining bright. We see near it the red Nergal, which is Mars, above it. Then ambling towards our destination, we feel the soft crunch of dewy grass beneath our bare feet as we walk along the starlit shoreline. We breathe in the calm morning air, and as we walk, we look directly up to gaze in awe at the glowing river of stars called the Milky Way. Now, standing out among these are the two greatest of the wandering stars, the ringed Ninurta, which is Saturn, of course, and then the god of gods, Marduk, which we call Jupiter today. We see them beaming down approvingly upon us. Nice. A few minutes more, and we've arrived at our suitable outlook over the banks across the prairies facing east into the dark, early morning. We wait patiently but excitedly. Then gradually we see the Paleolithic black, starry night gives way to the first glow of dawn. with it. So let's draw our little burgeoning sunrise. Right before the sun rises, we're going to see Mercury. And there it is. So it's brilliant. Its sharp radiance is only slightly tarnished by the ambience of the coming sunrise. And just imagine beholding this, the swiftest, most ephemeral of planets, Naboo, which we call Mercury, as it convenes with the other four in the twilight of this ancient sky. For just a brief hour before the break of day, the planets have aligned, and we've just witnessed an awesome phenomena that may not come again for another generation. And this is the emergence, the convening of all the stars in the night sky all at once. And just imagine what that would have been like for some Mesopotamian in awe of the night sky. No telescope, but maybe some rocks, some monolithic, some structures aligned so that he knows where to look in the night sky for these celestial beings. That would have really been something to behold. Now, although there's no firm evidence of the original discovery of the ancient texts of Mercury, the first mentions of it appear to be from around all the way back to 3000 BC. That's 5,000 years ago, by the Sumerians in this area here, Mesopotamia, which now is Iraq. So we're going to draw our little ziggurat. There we go. The first, that we know, the first official observations of the planet Mercury are found in something called the Mole dot Apin, which is something just used to refer to these ancient texts. They were a set of tablets, a compendium of astronomical and astrological, because they were fused at the time, knowledge made by their descendants, the Assyrians and the Babylonians, rather. The Assyrians were a real big empire. Babylon was, as far as I understand, along the Persian Gulf at the southern end of Mesopotamia there. Now, in these tablets, Mercury is called the jumping star, the jumping planet, no doubt due to its dramatically fast movement relative to the other planets. All of these, all five of these, they do move with respect to the more static, stationary, more predictable, more cyclical background of stars. But, Jupiter and Saturn being the furthest away of all these, they move the slowest, so they do proceed across the sky, and they all do their loops. But Mercury is the closest to us, and it's the closest to the sun. And so it zips around the sun faster than any other planet, as we'll talk about in a little bit. But from Earth, from our vantage point, that also makes it the quickest to pop up and dip below the horizon. If you can imagine, we have a little peak below the Earth, and this is the sun right here, just below the horizon. Mercury is the closest to the sun, so of course it stays the closest to the horizon. Let's just bolden the Earth real quick. There we go. And they called it the jumping star for that reason, because it's so quick, even relative to the other planets. Now, about 500 years later, by about 1000 BC, Babylonian astronomers had identified Mercury with the god of wisdom. And the associations of wisdom are literature, poetry, and knowledge in general, pre-scientific kind of knowledge. And this was the god Nabu. Now, Nabu was important because it's the home planet of Padme and the great Jar Jar Binks. Just Misa kidding there. Misa kidding. I had to throw that in there. You guys know that. Actually, Nabu seriously is, it began as a minor deity in the Mesopotamian pantheon of gods. He was just initially just a mere scribe to the great god of gods, their version of Zeus or Jupiter. But Nabu gradually ascended the hierarchy of Mesopotamian gods until he was depicted in later Babylonian art, actually riding Marduk's protective dragon, at times even superseding the importance and prestige of Marduk himself. And this is no doubt a testament to the growing importance of the transmission of written knowledge back then. That was the increased worship of wisdom over power, sheer strength of Marduk was kind of a metaphor for the growing importance of relaying information in its written form and the attainment of wisdom. And then moving another 1,000 years forward, maybe around 500 BC or so, Nabu's cult had actually expanded from the crucible of civilizations on Earth, all the way down to Egypt, west, through Israel, and planted its seeds kind of all around the eastern Mediterranean and the ancient world. So there's bits of that, as we'll see, all around. In, Egypt, in the pyramids, so it became, there actually was a cult in Egypt worshipping Nabu for a little bit. And then in Israel, there's a lot of evidence of Nabu's transmission. In the Bible, in Isaiah chapter 46, verse 1, for instance, Nabu is transposed into Nebo, designating someone who lived or was of Babylonian heritage in the Israel vicinity. And this is also the root of the mighty biblical king Nebuchadnezzar. You might remember that's Morpheus's ship in the Matrix. And so, over thousands of years, this god, it didn't die away. He was just transposed into different forms and different names. From the southeastern Mediterranean, moved northwest the worship of Nebo and his associated planet, remember, was again shifted across the Aegean, now into Greece, and he was to be fused with Apollo, the god representing poetry, reason, and knowledge. And you can see there's a little bit of an overlap, right? So we'll draw our little Parthenon. Maybe we'll make it go over the horizon there. But because the ancient Greeks actually thought that Mercury was two planets, again being the jumping planet, it's moving so fast. They called it Apollo when it was visible in the morning sky, and Hermes, the messenger of the gods, when it briefly popped up in the last rays of the setting sun. As the sun set. At dusk. Hermes became associated with his half-brother Apollo when he stole Apollo's precious cattle one day. And upon being called out for his theft, he actually invented the stringed instrument known as the lyre, L-Y-R-E, gifting it to Apollo as compensation for the theft of the cattle. Then Apollo, in return, actually gave him a caduceus as a gesture of friendship. And this is represented as... can shift this around now. This is represented as a staff with two snakes twirling around it, and this is the modern, let's see if I can, no, I don't want to draw it there. I got plans for that spot. Let's see, let's just draw it right here. Where you can see. And there we go, the caduceus. And this is a gesture of friendship. It's an astrological symbol for Mercury. But it wasn't until about the 4th century BC that ancient astronomers in Greece realized the two morning and evening stars were actually one in the same. And as Apollo was already linked to the sun, the Greeks eventually came to know the planet only as exclusively as Hermes. The Romans after them then, because, they were focused on more earthly pursuits, like expanding their empire, they simply maintained the status quo, and their version of Hermes was Mercury. So, over here we have our little Colosseum, I guess. Alright. So in other cultures, as far as that goes, Mercury is well known as well. The ancient Chinese, they called it the hour star. The Hindus and Germanic peoples associated it with Wednesday, actually. The idea of the week, as you can imagine, is actually very, very ancient, because if anything, the period of the moon is about every 28 days, so the idea of a 7-day week, cyclical week, has been around for a while. And the Hindus actually named it after Buddha, and the Germans, they named it after their god, Odin. Even the Mayan civilization in Central America, they knew it as an owl, the bird, and it was also, interestingly enough, a messenger in the realm of gods. Their owl was a messenger to the underworld. So that about takes care of the history of Mercury, and now it wasn't until after Christ, after the first millennium AD, the dawning of it at least, that the first truly scientific speculations began to give us a deeper understanding of Mercury's nature, as opposed to the, I would say, primarily psychological projections onto it that we've so far discussed. Around AD 150, the Roman-Egyptian astronomer Ptolemy, he wrote about the possibility of planetary transits. So now I'm going to move over to this side of the page. And, I actually didn't mention this, but this being Earth, of course, and this being Mercury, they're actually to scale, roughly. So when we think of the size of our planet, Mercury is bigger than our moon. Our moon might be like that big. But, of course, the sun here is certainly not to scale. But Ptolemy thought maybe, because we could see Mercury over here moving so fast, he assumed, correctly so, that it was much closer to the sun than most other planets. But he was wise enough to know that it was so small relative to the sun that, or at least so dim and small, you probably wouldn't be able to see it. And he was right. Without telescopes, you certainly can't see it transit the sun. But his speculations were certainly planting the seeds for future science. Now, 1,000 years after this, so around, 1100 or so, the collapse of European civilization, the petering out of the Roman Empire from, all the way to 300 AD, all the way to 700 or 800 AD, left a huge lapse in academic, intellectual achievements in Europe. And thankfully, the Middle East, there were kind of I think it was called the Islamic Golden Age. They actually were a wealth and a nexus of cutting-edge science and philosophies and ideas. The word algebra is a root word of a famous Islamic mathematician, and a lot of our words that we use today are derived from this era. So much of our ancient knowledge of even the Greeks and Romans is only wisdom that we've been able to extract from the texts of the Muslims and Arabs around the Middle Ages that preserved, because they were such a huge trading hub, that they were able to preserve these texts in their Arabic. And then later on, during the Crusades and afterwards, when we regained economic relationships with the Middle East, we were able to extract the previously lost information of maths and philosophies and whatnot, great literature that we had lost in Europe. So that's interesting that we are in the debt of the Islamic Golden Age. There was an astronomer there, an Islamic astronomer in the Middle Ages called Abu Ishaq Ibrahim al-Zakal that predated modern astronomy he actually described Mercury's orbit as highly elliptical, kind of like an egg shape. So I'm going to draw this. So if we have our little sun right here, and maybe we'll make it bigger. So Al-Zakal, or Al-Zakali rather, predated astronomy by recognizing that it orbits the sun much like the shape of an egg. I mean, planets at that time, if they were considered to orbit the sun, they were assumed, like all things in the celestial sphere, to be perfectly circular, to be perfect in all respects, perfect spheres, and perfectly undergo circular orbits. Because, of course, the cosmos was associated with divinity, so they wouldn't accept anything less than perfect geometric shapes. So Al-Zakali was far ahead of his time for this. So the closest point and the furthest point here is called perihelion, and this is called aphelion, are drastically different from all the other planets. And then 200 years after that, an Indian astronomer, going over to India now, way over here, over the horizon, named Nilikanta Somayaji, developed an interesting model of the solar system with Mercury orbiting the sun. But the sun in his model was still orbiting Earth. But nonetheless, at least he got it half right, you know? Because many of the planets back then, again, Earth was the general philosophy of the cosmos was that Earth was the center of everything. So it was a geocentric model of the universe. And this model was eerily similar to the famous Tycho Brahe, the, I think, Danish astronomer, a couple hundred years later. But it was a good seed to be planted about Mercury's orbit. And then in the 1600s, moving forward another couple hundred years, Galileo was then the first to see Mercury through a telescope. But his lenses, of course, weren't yet powerful enough to witness the slight phases of Mercury that existed. However, within a decade or so, the first decades after Galileo decided to point his telescopes up to the heavens, other astronomers had observed both its varying phases and a multitude of transits across the sun. And this is a pretty interesting thing. About 100 years later, after all that, 1737, an astronomer named John Bevis actually had the extremely rare opportunity to witness what's called an occultation. And this is where, let's see if we can do this. We have Mercury. We'll go back to this perspective real quick. So we have Mercury and Venus. Mercury is closer to the sun, so its orbit, even from Earth, is inside Venus's orbit. And then right here. So, let's see, we'd have Venus would be like this. It's got a little phase like that. And then here, so an occultation is where the orbits of Venus and Mercury from Earth's perspective actually overlap, so that Venus actually covers up Mercury perfectly. And this would be, so Venus right here with its back to the sun now. And that's Mercury. And Venus perfectly covers up Mercury. And this would be a pretty cool thing to witness, I think. But this guy, John Bevis, discovered, he witnessed it, but then realized that it only happens about 2 or 3 times a millennia. So it happened in 1737, but it sadly, for us, won't take place again for until the year 2133. So I'm sure it'll be cool for some of our great-grandchildren, maybe. So now we've kind of gone over the ancient history, the etymology of the name Mercury, the mythology behind it a little bit, and the early smatterings of science that have been useful in describing some of Mercury's characteristics. Now let's get into the more modern science. We see after science really took off around the year 1500, roughly, especially in Europe, astronomy expanded much more quickly than any time before that, really. And among some of the most tantalizing questions was the length of Mercury's day. Now, because Mars has prominent features we could witness hundreds of years ago through telescopes, and Venus also was, it was much brighter, so we could at least see the phases of Venus, but it was kind of a haze for a while, so we couldn't see its day either. But Mercury, it was kind of tantalizing. We had assumptions that because it was so close to the sun, it must have some unique characteristics that the other planets didn't have. Maybe only one side faced the sun at all times. And we were really curious about that. And the question actually remained unanswered for centuries. And this was due mostly to the interference of the atmosphere on Earth. Because our Earth, because as you know, our Earth has a really thick atmosphere. Nowhere near as thick as, say Venus is, but certainly much, much thicker than Mercury and Mars. And that makes the seeing, as astronomers call it, very terrible around the horizon, because as you're looking here in this direction versus more directly up into the sky, you have much more atmosphere to actually have the light rays travel through, so they get obscured. There's a lot more atoms, a lot more molecules for the light rays to diffract, to bounce off of, and disperse and diffuse, making the image much less sharp. And that was why we couldn't get a good visualization of Mercury for a while. And even in the 1800s, they had huge telescopes, these ground-based telescopes. They were like, 15 feet across, or at least like 10 feet across. These were massive telescopes. They could see Jupiter's spot, they could see Saturn's rings easily. But they could not make out Mercury for the life of them. And it took 20th century technology for astronomers to finally bounce radio waves from the Arecibo telescope. The Arecibo telescope, all the way around the other side of the world, was able to bounce radio waves off of Mercury, and they were able to see for the first time some actually geographic features like craters and valleys on Mercury. This was important because it means that they could now see how long it takes for Mercury. Now we can finally draw something here. So if we have a kind of a crater, I guess I'll make it a little more elongated like that. If we have a surface feature of Mercury, we know how long it takes to rotate by timing how long it takes to see that same feature rotate once around and come back into view in the telescope. And so it was cool. Now that we could see what the rotation was, we understood that Mercury actually didn't have a tidally locked orbit around the sun like the moon does with us, where we only see one side of its face at all times. By the 1960s, astronomers could see many unique characteristics. There were a lot of things about it that were primarily due to its very close proximity to the sun. They noticed Mercury's highly eccentric orbit, where it's up to half the distance from the sun. Here, let's see. It's 43 million miles at its furthest point from the sun, whereas its closest point, it's only 29 million miles. Which this is a drastic difference. It's the most eccentric orbit out of all the planets. And they also found that Mercury, going into the rotation now, This is probably one of the most interesting characteristics of Mercury here. Its rotation. There's two types of things we call days. Mercury rotates for something to rotate once on its axis. So this lettering, for instance, the time it takes for that piece to go all the way around, that's one rotation on its axis. And that takes about 59 Earth days. And its entire orbit around the sun, all the way around here, is about 88 Earth days. Pretty close to exactly 1.5 times longer. And this means that its orbital rotational resonance is a 3-to-2 resonance. For every 88 days, Mercury rotates 1.5 times. So that means for it to rotate an even a whole number of times, it has to go around the sun exactly twice. So its orbits aren't actually very chaotic. They're actually in a very tightly locked 3-to-2 resonance. That means that every 3 days is 2 years. So this is the same as its year versus its sidereal day is what that's called. So the interesting part here is that this isn't its day in the sense that we know the day, meaning from sunrise to sunrise. And here we're going to make a distinction between a solar day and what's called a sidereal day. The sidereal day, in essence, is how long it takes for a spot on the planet to point back up into the heavens. We use the stars as an analogy for a fixed point in the heavens. And let me draw this out for you. It was hard for me to understand. There's a difference between, let's see, if we have the sun, this is the sun, obviously, right here. We have Mercury facing the sun. So if we have a spot on Mercury, let's a spot on the ground, let's put that there. For it to rotate once so that this spot turns all the way around. And you know what I have? My little here we go. Okay. So I used an old racquetball with a pin and a small screwdriver in it so I can do this. So we have our lighting a little bit different now. I lit a candle here. So we have an idea of what's going on with Mercury's day. And just right up front, its day, there's a distinction between it rotates once, that's 59 days, but its solar day, what scientists call the sunrise to sunrise, is 176 days, or 2 years on Mercury. And that's due to the fact, very simply, that Mercury rotates so slowly with respect to its orbital velocity that the sun appears to never really set, or at least takes, again, years to make its way all the way around the planet. The reason I busted out this candle is because the 59-day rotation is called a sidereal day. This is from the Latin word sidus or sidus, I'm not sure how to pronounce that, for star. This is the primary way astronomers define the rotation of any cosmic object. This is the rotation relative to the stars that are essentially fixed points in the sky. So it's a reliable measurement. So for scales of time on the order of hours, days, or even a few years, astronomers treat the constellations, whether it's Orion's Belt or the Big Dipper, as though they are permanently fixed on a almost infinitely faraway sphere. So you can imagine we have our sun and our planets going around it, and then almost infinitely far off in the distance, it's like a big glass sphere on which the stars are painted. And if you're a fly on that sphere up here, and you're watching all this action going on, you don't move relative to the extremely rapid rotations of all the planets, and the orbits of the planets, and comets, and everything going on inside our solar system. So from this perspective, if a point on the planet Mercury is out here, let's say this is the sun, so we'll say out here is a constellation. The time it takes for a point to rotate and point directly back to that constellation is called a sidereal day. Now this is way different than a solar day. And let's see see how I wrote this in my little script here. Let's see. So in Mercury, sidereal day. Okay. And so this is representative of a sidereal day. Let's pretend there's some bright light off in the distance, the stars. This has been 59 days from here to here. Now, if you can imagine, you could see it's undergone its subtended an angle in its orbit. So the sun is now actually, Mercury is now in a different position relative to the sun from when it first started. By the time 59 days has passed, it's undergone about 2/3 of its orbit. So for planets like Earth, there's a small difference, but there is still a difference. For this point that has rotated all the way around, and seen the same star in the sky again, for it to rotate so that the sun is back in the same position in the sky, that it's going to have to undergo a slightly longer rotation. So the sidereal day, meaning a star or a constellation returns to its exact point in the night sky from one day to the next, one rotation to the next rather, is going to be shorter than for that same point to rotate and then rotate a little bit more to make up for the difference of its position relative to the sun now. So that little distinction, this being the sidereal day, this being the solar day is what accounts for Mercury's sidereal day being 59 days and its solar day being 176 days, or exactly 2 of its years. And if let's bring this camera, I'll try not to burn it. Maybe we can look at it like this. So Mercury is rotating. It's not exactly like this. The point on Mercury's surface, it doesn't exactly look, it doesn't face the sun all the time, but it's slow. So it takes, if we start exactly right here, it undergoes a complete rotation to return back to that direction. It takes about 2/3 of its orbit to do that. So as the sun dawns for this guy right here, now we see for him it looks probably like it's kind of morning, now late morning, and by the time it goes back to its original position, it's maybe mid-afternoon. Slowly the sun's almost setting. It's getting there. And now in another 2/3 of its orbit, remember it's going to go 3 full rotations in 2 orbits. It's a 3-2 resonance. So once more, just because I think it's so cool, we have the sunrise on Mercury, and you can watch it. Imagine where the sun would be. It's like early morning, kind of late morning right there. And it's kind of like midday almost. And right there, we're returned to our original position. About 2/3 of its orbit is now complete. We need to get back here. So the sun is now it's hit its peak, and now it's kind of starting to set. And as we continue through another 2/3 of its orbit, the sun's just about to set. And there we go. Looks like the sun set. And now we're at nighttime here. Another 2/3 of an orbit has completed. We already hit our year, and we're about 1/3 into the second year. And then we've completed 2 rotations already. And we need 3 full rotations in the same time it takes to complete 2 orbits around the sun. And our last final rotation, as we try to have our little tack, we see about right here, if you can imagine it. Do that one more time. So it's like nighttime, and then it's rotating around, and right about here is dawn, sunrise coming up. But it's orbiting so fast that the day just takes that long to complete. So the reason Earth doesn't have a real big distinction between our sidereal day and our solar day is because that little difference right there is only about 4 minutes. So for us on Earth over here, our solar equals pretty much 24 hours, and our sidereal is 23 hours, 56 minutes, and a couple seconds, something like that. So in 23 hours and 56 minutes, we've returned to looking at the exact same star. And then 24 hours, 4 minutes later, we've returned to looking at our sun because we've undergone a little bit of our orbit, only about 1/365th of our orbit. Whereas Mercury, it undergoes, you can imagine, 2/3 of its orbit by the time it's rotated to face the same star in the sky. Now let's see what else. And we're going to talk about a couple different features about Mercury and the Sun. In fact, so the Sun has two characteristics that make it drastically different than what we experience here on Earth. Because Mercury's orbit is so eccentric, it comes out here, and you can imagine it's pretty intuitive when you think about orbits. The speed as it's receding from the Sun. So let's make our Sun a little bigger. As Mercury goes away to its aphelion, its furthest point from the Sun, which remember is about double the distance from its closest point, you can imagine it's losing a lot of gravitational potential energy. The Sun is trying to get it back to its closest point, but there's no air molecules in space to slow it down as it moves. So the orbit is taking billions of years to slow down slowly. But within each orbit, Mercury is slowing down here and then gradually speeding up and zipping around. Speeding up, zipping around like that. That's kind of what it's doing every orbit, every single orbit. Let's see. And the cool part here, what I really like is to imagine, is the sheer size of the Sun in the sky. So I think, so if we compare the distances of the planets from the Sun, again we have, let's see, so if we have the Sun, we got Mercury right here. We got Venus out here. And we're all the way out here. Well, I guess that's not to scale, but the Sun would, if the planets were pretty much the size of atoms, or like little, cells, single-cell organisms, maybe that might be to scale with the size of the Sun right there. But just imagine the size of the Sun in the sky. Well, for Mercury, the Sun, let's see, the Sun for the Earth, there's a really cool diagram. For the Earth, if the Sun is about, Sun's about this big in the sky, and it is about right. Usually when you hold your thumb at arm's length, it pretty much covers the Sun from, obviously, Earth. And Venus and Earth are in elliptical orbits as well, but to give you a perspective of just how much more eccentric Mercury's orbit is, our perihelion and aphelion Sun, you can't really notice the difference in our suns. And Venus is a little bit closer, so I think its Sun looks something like that in its sky. And then of course its perihelion being, again, the closest point to the sun in their orbit is really only just a small bit larger. Now, Mercury it's right up next to the sun. So at aphelion, its furthest point in the sun, from the sun, it looks something like maybe, I don't know, about a diameter about twice as large. As what our sun looks like. So this is Mercury at aphelion. And now, when Mercury swoops in right here, it gets twice as close to the sun. It gets 5 times closer to the sun than we are at our closest point. Its sun looks, I'd say, maybe not quite that big. Its sun is about right here. Perihelion. Just imagine looking up in the sky, and we have our sun right here. And then we look up in the Mercury sky and see a sun who in area takes up 9 times what we see from here on Earth. So if we're on the Mercurian surface, this sun is over here, dominating, just absolutely dominating the sky. So, Jesus, that's just, I don't know, it's incredible. It's got to be pretty amazing to really imagine being that close to an object that is just oozing with bursts, continual perennial bursts of nuclear fusion, matter being fused together and releasing billions of kilotons of energy every single second. Just imagine being that close. So it's huge. The sun looks huge in the sky, and it goes from about 4 times what we'd see in the sky to about 16 times the area of that our perspective of the sun in our sky takes up. So over a period of about 8 Earth days, as it speeds up, the sun, of course, is growing from this size to this size. But what it's also doing, it's taking, if it takes 1 full year for the sun to traverse half of Mercury's sky, it's going to take 44 days to get from aphelion to perihelion for Mercury's position in its orbit. That means from about morning until about noontime, Mercury's sun is going to go from here to here, 4 to 16 times what we see on Earth. And in fact, as it gets to perihelion, Mercury is speeding up around the sun, and the sun actually begins to reach a standstill, because most of the time its rotation is a little bit faster than its orbital velocity. But because it zooms in so fast, when it reaches perihelion, its rotational velocity is not quite able to keep up with its orbital velocity at that point. And what ends up happening is really got to be a sight to see. The sun appears to actually, for over a period of 8 days, slow down to a standstill for about a day. Could almost picture it like this. The sun goes until it slows down, hits perihelion, pauses, and actually goes backward in its motion until finally it comes out of its gravitational whip around the perihelion and starts slowing down again, in which case the sun, the rotational velocity will again catch up to its orbital velocity and overtake it, allowing the sun to return on its trajectory across the Mercurian sky. So you can imagine the sun would go and slow down, start to go back, and then continue on its motion towards sunset. So, to recap, a year on Mercury is 88 days. A sidereal day is about 59 days, 2/3 of its year. And then, because it's moving so rapidly around the sun takes 176 Earth days, or 2 years of Mercury, to go from sunrise to sunrise. In this little thing called the perihelion, it actually underwent a precession, so I'll do a miniature version of it here. It was actually important in proving Einstein's theory of relativity. This is pretty cool. Despite the sidereal solar day distinction being, kind of weird to grasp at first, it's actually pretty well understood phenomena by astronomers. It's the same reason that our moon is tidally locked to our Earth. It's called gravitationally or tidally locked. It's just where one side faces its gravitational tyrant, if you will, at all times. And Mercury is approaching that, so eventually its rotation will slow down to the point where it will have just one side facing the sun at all times. But what's not so nearly as understood, at least it wasn't for hundreds of years after Mercury was first studied by Kepler in the 1600s, was this weird motion. Let's see. So Mercury has this general shape, but what we found out was that because it's so close to the sun, its orbit was doing a weird thing called a precession of the perihelions, or a perihelion precession. It was where the point of its perihelion was dancing around the sun. So every orbit, it got a little bit more offset. For nearly 400 years, astronomers were completely baffled at this phenomena. Kepler and Newton's equations all made sense for all the other planets. They predicted their orbits nearly perfectly. Certainly, perfectly and accurately enough to where there was really no question of the validity of the equations. But Mercury's orbit was always being a little bit offset, and no one could figure out what it was. And this perihelion precession actually even led one famous 19th century astronomer and mathematician to posit a planet called Vulcan. This guy was Urbain Le Verrier. He was actually the discoverer of Neptune. So he had a lot of respect in the community for discovering Neptune, so people listened to him. And he thought there must be another mass right inside here, ridiculously close to the sun, that was pulling on the planet, perturbing its orbit just a little bit. But for over half a century, he went around and actually gave lectures on it, talking about a new hellish planet. He won some brief acclaim for it. Ultimately, the existence of old Vulcan was never quite verified. I'm sure that didn't prevent him from living long and prospering, though. It took the application of Einstein's new physics about 100 years after this guy was trying to posit a Vulcan, a very volcanically active planet, and running with it. It took until about 1915, 10 years after Einstein put forth his special theory of relativity, for astronomers to solve this mystery. And this was actually before the eclipse of 1919 that I believe the eclipse of the sun, it was eclipsed, and the light from around it was able to be detected bending due to the sun's immense gravitational field. So what astronomers came to understand was that Mercury's distance from the sun meant that it was so close and so enveloped in its gravitational field. The equations of Newton that described all the other planets so perfectly actually breaks down. So let's see if we you can imagine here just like on all those TV shows. And so the sun, it's like it's in its gravitational well. And Mercury is close enough to be kind of trapped in it as well. It's almost like on Interstellar, when they were so close to the black hole that, of course, that was a gross exaggeration, but the time on the surface of the planet was equivalent to every hour was some crazy, like 7 years or something. But yeah, way out here, for Earth, the gravitational well, it's still trapped in the sun's gravitational well, but it's experiencing much less of these relativistic effects that Mercury's undergoing. So I thought it was pretty interesting that at distances beyond, the orbit of Venus and Earth and whatnot, you don't need Einstein's relativity equations. Newton's equations work just as well. But it's when you get a severe warping of space-time that Newton's equations they break down, and they can't account for the variations in the space-time continuum, I guess. And if we wanted to impress someone at a dinner party, what you could say is that all of Newton's laws are accurate thousands, tens of thousands of years into the future for all the other planets except Mercury. Because, maybe I'll sound like Wesley Crusher here, because the gravitational perturbations in the space-time field around them, they have negligible relativistic effects. And so it's only for very strong fields that general relativity has to be used to really understand and predict the motions of the planets. I think one equation I found was a partial differential equation, r cubed. There we go. Couldn't quite fit that in there. So it was really cool that relativistic effects cause the actual rotation, the orbit itself, to rotate. So the planet's rotating, and it's undergoing an orbit, but the orbit itself is rotating like that. So it's super cool to think about. I'm just fascinated by how we have these geniuses like Einstein and Newton, and we can predict and accurately predict these fundamental laws of nature. It's just amazing. So we've been clearly dancing around the planet itself. We know the history, the early science of it, some cool, some characteristics of its orbit. Now let's go ahead and touch down, on the surface. So after the Earth, Mercury is the second densest planet. It's denser than either Mars or Venus even. And despite being smaller than the moons Ganymede or Titan, it's incredibly massive, much more massive than any moon in the solar system. Its huge core, actually, so let's go ahead and draw this, is 85% of its radius. So we're going to do this. We're going to draw its thin crust. And then we're going to draw its core. So just imagine the core of our planet is something like 15% of our planet. You wouldn't even see it in this picture here, as far as the radius goes. But Mercury's is 85% of its radius from here to here, it's 85%. And by volume, it's 40% of its volume. So it's almost half the entire, not the mass, it's most of the mass, but it's almost half the entire volume of the sphere-like object. So let's try my best. Luckily my little bumps are helping me make it look kind of accurate. Because we all know a planet is not perfectly smooth. And we'll just highlight these lines a little bit. Alright, that's pretty good. Because we want the star of the show to be notice and recognizable. So the core, 85% of its radius, 40% of its volume. So we have the mantle. Oh, sorry. Kind of messed up on that, but this is the crust, the mantle, and the core right there. And the core is, as you can imagine, you know, in any compound, any mixture, heavy objects, heavy materials like metals are always going to sink down to the bottom. And in the solar system, in that same way, the bottom is the center of the gravitational well that we, in our solar system, is the sun. In the Milky Way, it's the black hole around Sagittarius A star. And of course, so everything that didn't fall into the sun would have formed densest and heaviest, closest to the sun. So that's our four terrestrial planets. We call terrestrial meaning terra firma, meaning Earth, and they are rocky planets, as opposed to the four gas giants that we all are pretty familiar with by now. And so the core is made up of mostly iron and all these heavy metals. Because of that natural tendency for heavier objects to settle in closer to the bottom of any gravitational field. That huge core means that a lot of the magma is flowing relatively just beneath the surface as well. And I don't think it's still very active volcanically, if at all. It might not be. It might not be very much. But that magma as a slip definitely affects different things like the magnetic field, the heat, even the size of the whole planet. In fact, astronomers have concluded that over 1 billion years, the magma making such a significant part of the planet, as some of the magma might have escaped somewhat a little bit, and just generally being so close to the surface, being so exposed to space. In the absolutely ridiculously freezing temperatures of space, it generally cooled the planet. And when you have cooling, everything except ice, contracts when it cools. It gets smaller. So what that means is that the planet actually has shrunk by up to about 4,000 miles in its diameter. As the heat is lost to space, the planet itself actually shrinks, which is pretty amazing. The magma cools, and the crust contracts. Now, as for its atmosphere, it has a lot of mass because it's so dense, but it's still, still a little guy. It has just 38% of Earth's gravity. And because of this, what might bounce like this on Earth, it's over here bouncing probably 3 times as high on Mercury. It has roughly the same gravitational field as Mars, actually, which is way bigger than Mercury. So that's pretty crazy to think how much a dense planet, a densely heavy metal planetary core can act as a gravitational source. It's pretty cool. So that'd be Earth. And this is Mercury's gravity right there. And because of this light gravitational field, even though it's, relatively for its size pretty strong, it hasn't been able to substantially attract, of course, any moons or rings, but also any atmosphere, any significant atmosphere. The mercurial atmosphere is actually so thin that it's closer to a true vacuum than anything we've been able to artificially create here on Earth. Now, there's still a measurable atmosphere, but the density of air molecules is so thin that it was a pretty cool statistic to realize that our space station is about, I guess, 250 miles, I think, miles in altitude. Well, Mercury's surface atmosphere is as thin as not what's up in the space station, but double that, almost triple that, over 600 miles out of the Earth's atmosphere, or rather in altitude away from the surface of the Earth. 600 miles is equivalent to the surface of Mercury. So the space station is traveling at something like 17,000 miles per hour. There is pretty much non-existent atmosphere. And so you can imagine how unimaginably thin, I guess. So maybe you can't imagine it. It's ridiculously thin. It's insignificant and certainly not enough to retain any substantial heat, or and definitely not erode any craters or any geological features like the very dense atmosphere on Earth here does. And we'd think, just like Vulcan was supposed to be just this searing hot planet being that close to the sun, well, Mercury's not much further away than they thought Vulcan was, actually. So you would think it's definitely, by far, the hottest planet in the solar system, right? It is pretty dang hot, the side especially that's being melted by the sun, going up to something like 800 degrees Fahrenheit during the day. So this is the side that's being blasted by the sun is 800 degrees Fahrenheit. But that actually is cooler than the surface of Venus, which is actually the winner of the hottest planet award. And I guess that's pretty appropriate, given the fact that Venus is the goddess of love. And that's due to her special features, being her thick, voluminous atmosphere acts like a super efficient insulator, keeping most of her heat in. So that explains why Venus outcompetes Mercury for the hottest planet award. And Mercury's lack of atmosphere also exposes it to extreme temperature changes. So during the day, as it's being bombarded by the sun, it's up there at 800 Fahrenheit, but during the night, after a mere 44 days, once it does eventually set, its temperature on the other side, the dark side, goes all the way down and all the way around the other side of the planet. At night, it has no atmosphere, remember? So immediately, all that heat, even the insulated heat in the crust that the crust has absorbed in the molten rocks, they're sitting there at 800 degrees. After a couple weeks go by, exposed to the dark, cold, still recesses of space, it drops all the way down to something close to negative 280 degrees Fahrenheit. And so we have something like a couple miles of thick atmosphere here on Earth that prevents all our radiation from leaving. Whereas they on Mercury, they have no atmosphere to really insulate them at all. So all that heat is lost immediately. There's nothing preventing it from scattering off the planet and receding into space. So though Mercury's magnetic field at the surface has really only about 1% of what Earth is, it greatly still interacts with the magnetic field of the solar winds. Being so close to the sun, being 5 times closer to the sun than we are at its perihelion, Mercury is undoubtedly bearing the full brunt of the force of these solar winds. So Mercury is pretty small, but it packs a punch with its heavy iron core. A lot of iron in there. It only has about a magnetic field 1% of what Earth's is. That still greatly interacts with all the solar winds that are always barraging it. And this sometimes, interestingly, creates funnels. Creates these magnetic field funnels So it's pretty wild. Its magnetic field is actually offset from its core. I'm not really sure where I wrote that down, but its magnetic field is kind of doing something like this. So we get this funnel effect of these solar winds hitting the field and then being funneled down to its surface, where it actually strikes the actual surface, knocking off neutrally charged atoms and sending them on a loop high into orbit. And what happens here is that any little atmosphere that Mercury might have had is kind of knocked away, and as it's washed over by the solar winds, the very charged, highly charged particles being emitted from the sun at all times, these are the things that interact with the oxygen, nitrogen, and other chemicals in our atmosphere to create auroras at our poles. And so it's constantly having its atmosphere replenished, if you will. So as it washes some away, it knocks off other negatively charged particles, or neutrally charged, charging them negatively and sending them over, up and away, spiraling into the altitudes of Mercury, to create a very flimsy atmosphere. Now, the surface, I already kind of made a little crater right there, because Mercury is distinctly, very visibly covered in craters. Like we said, it has no real volcanic activity to smother and smooth over any of these rigid, rocky surfaces. And it has no real atmosphere to erode away, even over millions of years, even billions of years even. No real atmosphere, no wind, no rain to slowly wear down and smooth out these craters. So they're just basically as sharp and vivid as they once were, or as they were from the get-go. The surface is similar to the moon's, so much of its scarring is actually due to ejected chunks of bedrock. So while we have many of its craters obviously made from meteoroids and comets smacking into the surface, what happens as well is that when this gets hit, maybe I can work around that. When it gets hit, you have, boom, you have these huge craters being formed. But what also happens is that the pieces, huge chunks of the crust itself, is ejected into orbit. Not quite orbit, but high up into the atmosphere, where it falls down all around the crater. creating secondary craters. All outside the primary crater. So a huge comet comes crashing in, ejecting chunks of bedrock, and they fly silently into the highest altitudes. Silent because there is no atmosphere through which the sound can travel. And then they're splashing down all around, forming new craters, new secondary craters. And sometimes even finer, more reflective particles from either the crust or the impact object are flayed out, and they create these streaks, these bright, bright streaks we call crater rays, almost looking like a bag of flour smashing into the surface. And you can visibly see these in a lot of the pictures of Mercury. One of the brightest spots is actually from a crater left around a 40-mile wide crater, the crater rays rather, called Kuiper, from the astrophysicist whom the Kuiper belt is named after, the series of rocks that Pluto is the innermost, one of the innermost of, and most significant of. And here, it's very important to consider the rapid speed around the sun that Mercury is orbiting at, and how this might affect the violence of a collision with another object. If you have a comet traveling into the solar system, and we have Earth over here, when it hits Earth, that's a violent impact. When it hits Mercury, that's a whole nother story, because Earth is over here doing a nice graceful orbit. Mercury's over here running like a dog chasing its tail. Its orbital velocity is so fast, especially when it's undergoing perihelion, that a comet smacking into it it's almost equivalent to something being hit by a car going 10 miles an hour versus maybe 80 miles an hour. The impacts are so much more violent, and astronomers actually, I read that astronomers actually think possibly the most violent impact in the entire solar system, at least the terrestrial planets, because we can't really see what happens in the gas giants once something falls into them, is possibly the Caloris Basin on Mercury. To give you an idea of the speeds, let's see, the International Space Station is traveling at about 17,000 miles an hour. The planet Mercury is traveling roughly about 100,000 miles per hour. This is incredibly fast. And comets, actually, once they get that close into the sun and they're reaching their perihelion, they're going to be reaching that same speed. And so to watch two objects colliding in a 200,000 mile an hour impact has got to be a sight to see. Back in 1975, I think it was, the first spacecraft to visit Mercury was called Mariner 10. And this discovered a huge, what's called a basin on Mercury. Now these are craters that are 150 miles wide or more. So you have small things, maybe a grain of sand, a rice, maybe a bus, maybe even the size of a stadium. But when you have things that are miles wide, you get planetary levels of geological impacts. And the coolest part about this is that this Calorus Basin, we'll say, it's this bad boy right here. And they think that it smacked Mercury so hard it reverberated and sent compression waves running through its core and the surface. So it's got these, so if this is it, it's got these waves emanating through its core. And so by the time these compression waves have rippled through the core, and then also through the crust as well. And they actually are gonna, with enough impact, it's gonna lift up the rock. It's gonna shake the other side of the planet. And that's actually what happened on Mercury. And this is probably the most astounding thing about Mercury that I found, was that there's a place they call the peculiar terrain on one part of the planet. It's made up of jumbled, chaotic hills ranging from 200 all the way to 2,000 meters, 2 kilometers high. And geologists believe that that's exactly what happened. It was compression waves rippling around the crust and through the core and meeting and converging and heaving up the bedrock in the crust into piles. And that kind of energy is very peculiar. And finally, I want to just discuss the most recent probe that we've sent to investigate Mercury's environment. And this was named Messenger, aptly enough, as Mercury is, of course, the messenger of the gods. It was launched in 2004 and stands for Mercury Surface Space Environment. EN for environment, GE for geochemistry, and the last R for ranging. So it was the Mercury Surface Space Environment Geochemistry and Ranging Probe. And this was launched on board a Delta II rocket to study Mercury's chemical makeup, geology, and magnetic field. While in orbit, Messenger actually concluded the presence of high concentrations of magnesium and calcium found on the surface. So I believe it's magnesium and calcium is Ca. I might be wrong though. It also detected another peculiarity about it. It was in Mercury's magnetic field. And that was what I talked about earlier. It appears to be offset to the north of the physical center of the planet by a significant amount. Now, I don't know what this means, but apparently neither do they, from what I could find at the moment. They just know it's a peculiarity of the magnetic field. Now, this probe met its fate in 2015, once it ran out of energy. Yeah, the Mariner, they think, is still in orbit around the sun at the same radius from the sun as Mercury is. But the Messenger probe, they specifically crashed it out of orbit. After 10 successful years of observing the planet, when it used the last of its fuel and subsequently fell out of orbit, crashing into the planet and getting a couple interesting pictures along the way. Now, before it crashed, it confirmed the existence of both carbon-rich organic compounds at its North Pole. So we're going to pretend that this is its North Pole right here. Because you have craters when the sun's hitting here at the North Pole, just like here on Earth, that the sun will never hit just due to the sheer angle at which the rays are hitting the planet. So you have some craters, most of which, they're never heating up. There's no atmosphere to trap heat on the equator and send it north. So these things are always exposed to the cold, near zero temperatures of space. And what they found was organic compounds and water. And this is really amazing. It's really something that happened. So that tells us that even on the most extreme planet, pretty much, other than maybe Venus, we have organic compounds in water ice, the stuff of life. This is fascinating because what it means is that the stuff of life certainly exists outside Earth now. We know that. And therefore very probably exists on many other worlds yet to be even discovered and certainly explored, both in and out of our solar system. So we don't know what kind of life is yet to be discovered. And that, my friends, is why Mercury is so interesting. Hope you enjoyed it. I guess this one ran a little bit long, but I had fun. It was a lot of new, interesting things about it. Gave us some more insight into our home neighborhood, the solar system, and intrigued and sparked my curiosity about just what else is out there. And certainly fuels our imagination for just how probable it is that life exists somewhere outside of Earth. Sleep well, guys, and we'll see you next time. Bye.